Right. So what's next? So once we draw the analysis, or other assumptions here, right? So we say delta H is 0, right? Delta H is 0. Delta PE is 0. Delta K is not, because obviously we feel there is a velocity here on this side. So now let's write the equation. So now if everything is done, then apply the equilibrium equation. Sorry, equilibrium equation. The energy equation. So apply the energy equation, or energy balance. You know. So energy in. Okay, so which form is it? The total? Is it the rate? Or is it the specific? So you notice that the unit here is in rate basis. That's in watts. That is actually power, energy per unit time. So this is power. So we need to use the rate form. So energy in minus energy out, right, is equal to the change in the energy of the system. So energy, the system, right? So of course with respect to time, right? So whenever we have a rate form, special case, or a simplified case, or specialized case, or in most problems that we'll encounter, we can say that steady, right, steady state, or I think I have also mentioned it here. So assume steady state conditions, so which means that the properties of the system does not change with time. State note is the property of the system, does not change with time. So the properties of the system does not change with time. So this is 0. So that means that the energy in is equal to the energy out. So I think because of this steady state assumption, that whether you choose the fan as your system, or the airflow that pass through the that passes the fan. So I think it's gonna be the same, because the this right side term is actually 0. Anyway, for this case, so F in, F out. All right. So what are the interactions that's going in? So it's the electrical work, plus this F in. So the flow, energy via mass transfer. So F in. So let's write it here. Work plus F in is equal to F out, right? So let me check it here again. So supposedly, what if our system is the air? So if the system is the air, then it has if the system is the air, then the delta is, I think it's the same. Sorry, delta E of the system. This is delta U plus delta delta KE plus delta PE. But since we have a moving, there's a next batch of air that's crossing our boundaries, then that means we still have this term here, F in, F out. So I think it's just the same thing, right? So let's delete that. So F in is equal to F out. Now I want to transfer this F into the right side, so work is equal to F out minus F in. And since this out and in is they're just actually the difference, so can I write it in terms of delta F, right? And what is the delta F? The delta F, recall from our topic 6 that it includes the that actually includes the U, of course, delta U plus delta KE plus delta PE plus the delta of the flow work. But since U plus PV, this is simplified to delta H, right? So plus delta KE plus delta PE, right? So that's it. That's the delta, or that's the those are the terms included in this delta F. Okay, so um, let's erase this. Let's erase. Right, so work is equal to delta H plus delta KE plus delta PE. And since we say that there's no change in the enthalpy, then that means this is 0, and there's no change in the potential energy. This is 0. But the kinetic energy is, there is a change, right? So that means we have this is total. Of course, we are referring to rate forms here. So delta KE is just simply 1/2 m v2 squared minus v1 squared, right? So it's just the change in the square. Sorry, change in the square of the velocities. So take note, these are velocities. Right, so velocities of what? So the v1 corresponds to the velocity of the inside air. So this is inside air. So exit or discharge air. Discharge air. So it's the square. And since this is in rate form, then that means that the mass is in rate form, right? So still air, also recall that still air is 0. This is assumed velocity is 0. So therefore, our equation would be work is equal to 1/2 m v2 squared, right? So we have the value of work, we have the value of m dot, then we can solve for v2 squared. So v2 squared, so v2 is just equal to the square root of work times 2 divided by m dot, and the value here is this is 6.32 or meters per second, right? So that's the answer. Okay, so for the units, of course, this is a unit of velocity. So that means we are expecting a unit of velocity that is in meters per second. So to check, this is a unit of power. So the unit of power is Newton meter per second, right? Times times 2 divided by the unit of mass flow rate. Mass flow rate is kilogram per second. Okay, so next is, what is Newton? So it's kilogram meter per second squared, right? Times meter per second, and here kilogram per second. So let's cancel kilogram, what else? A second and second. So what's left is meter times meter. So meter squared, second squared, and you take the square root of that, square root of m squared per s squared, you have a unit of velocity. Right, so I think that's all for this sample problem 7.4. If you still have time, then we'll move on to the next sample problem. Alright, so this will be our last sample problem for this use of energy balance equations. It says here water pump increases the water pressure from 15 psi to 70 psi. Determine the power input required in horsepower to pump 0.8 cubic foot per second of water. So recall that the subject of thermodynamics is all about the energy and its transformations, right? And although almost everything includes energy, but for us engineers, what we're interested in are those devices wherein we have these practical applications for the to provide industrial solutions, like for example pumps, refrigerators, air conditioners, engines, power plants, and stuff like that. So one of such devices is pumps. That is why commonly you will encounter this kind of problems, engineering problems. Right. So also another one is, I think in the previous video I mentioned about, I've said that fans blowers and compressors, they are actually fluid moving devices. So this also includes pumps. Pumps is also Pumps are also fluid machines, which means it transports fluids. But in the study of fluids, usually for fans, blowers, and compressors, they are used for gases or vapors or airs. Whereas pumps, technically, it's for liquid substances, or maybe slurries. For some types of pumps, we have slurries. That means liquids plus some, okay, plus some solids in it. So liquids plus solids, so slurries or liquids. So that's um, the concept behind these fluid moving devices. Now, pumps is, um, if we have here, let's say, an elevated tank. Let's say we have an elevated tank for a building water supply. So naturally, in terms of the direction of the gravity, or the pull of the gravity, the flow of water will be from higher to lower, right? So that's the common, or that's the natural direction of flow of water. It's from a higher elevation to a lower elevation. So it's a natural to be to move the water from a lower elevation to higher elevation, unless you are talking about the maybe some pressurized portion underground, and then that it bursts waters and it goes upward. Yes, because that's the it's actually the pressure. So there's a lot of pressure here as compared to the atmospheric pressure. So that's why it can shoot up, but you will notice that there's just a limit, so that it will go down. Right. So it's all about actually pressure. So that's the reason behind these devices, the pumps. So the pumps are devices that can increase the pressure of the water, so that it can transport the water from, let's say, from an underground source of water here. So you have underground source and transport it here to an elevated tank. So the direction of flow will be going upward, right? So that's the idea about the pumps. So now the question is, how does the pump increases the pressure of the water? So just like the fans or blowers, inside that pump, let's say here's our pump, and let's say we'll draw a centrifugal pump. So it's just one type, and inside that, what you can see is we have this shaft, rotating shaft, of course, and in the shaft we have this maybe a part of fan, a hub maybe. Then we have these blades, right? So we have blades here. So maybe on this view we have here, right? So we have these blades, and the water will transport from, let's say, from inlet to the outlet, right? So inlet um, going to the center, and then leaving here on this outlet, right? So it will go inside here, and then it will be hit by this blade. So it's about heating the fluid, so that, or imparting force, or imparting energy to that fluid by the heating of the blades, right? When I say heating, by the way, I mean heat, heat like this, heating or heat, right? So heat the fluid with the use of blades. So it's not heating like this. It's not this one. So I'm referring to this, right? So it's all about that. So imparting energy because of the blades heating the fluids, right? So in order for that blade to heat the fluid, then the shaft must be rotated, right? So this shaft must be rotated. So this must be rotated. But in order for the shaft to be rotated, there must be some source of power, which is maybe an electric motor. That electric motor again is connected to some electrical source. So that's the energy transformation in this shaft right here. Right. So I think we can now erase this introduction. Right. So, okay, we can erase this introduction. All right. So now let's move on to the analysis. All right. So first things first. So for the solution, we have first is draw the analysis. All right. So for the analysis, what is our system? Is it the pump? Is it the water? So I think I'll just use the pump for that. All right. So I will use the pump as my system, and then specify the interactions. Right. So we said that a pump requires work input, right? So the work input here actually is we can trace it back. So the work done by these blades to the air, and then um, uh, we can trace it back to the rotation here, and maybe at the end is the output, electrical energy required. Or, okay, so actually there are efficiencies involved here. So it's not, if let's say this is 20 watts, then everything here is 20 watts. So it's not actually that way. There's efficiencies, but for now we'll just use whatever knowledge that we have so far. Right, so it must need some work input. So let's just use this. So work input. So work input, that's actually what we're looking for, right? So determine the power input required in horsepower. So that's required, and then we have also a flowing mass. So flowing mass. So we have F in, and we also have flowing mass here. So we have F out. Okay, so here's our system, and for the state points, actually um, this is just a balance. There's not much data given. Anyway, um, oh yes, there's data. We have state one, right? State one and state two, but the data is only pressure 1 and pressure 2. Pressure 1 is 15 psia. So this is 15 psia, and this one is 70 psi. So that means that the fluid entering here is has a lower pressure, but once it's heat up, then it has an increased pressure. So here at exit point. Right, so what else do we have? Velocities. So in the previous example, we have a change in velocity because we have it's the air, actually fans, because uh, not much pressure as compared to the pumps and compressors. So that's why the pressure there is constant for fans. But for pumps, it has a higher pressure capacity, so that means we can see this significant change in the pressure. Okay, now in terms of velocity, yes, there is a velocity, but for now, we will assume that the velocity is constant. Velocity, maybe we'll write it here. So assumptions. One of the assumptions is that velocity is constant. Velocity is constant. So why is it constant, and how can it become a constant? Now, it can become a constant if the area here, or the diameter of the pipe, let's say if we use 2 inches pipe here and then 2 inches pipe, so it's just the same diameter, the same cross-sectional area, the same material, then everything else is the same flow rate. So I say 0. 0.8 here, 0.8 cubic foot per second, 0.8 cubic foot per second. So everything else is the same. That means that the velocity is actually the same. So later on, we will discuss this under the mass flow rates topic after this sample problem, right? So velocity is constant. So therefore, kinetic energy is, or the change in kinetic energy is zero, right? So I'm not saying that there is no velocity. What I'm just saying is that the change in the, or the difference in the velocities of the inlet and the outlet, they're actually zero. So, okay, next one is, okay, another assumption is the potential energy is, you can assume that it's zero. Why is it zero? Because let's say this is the inlet, right? And here's the outlet. There is actually a change in the height. So the inlet is right here at the center, and then the outlet is here at the tangent point, or at the quadrant. So there's actually a change in height, but it's not significant as compared to the, let's say if we have a problem dealing with dams. Let's say here we have a water on one side at this level, and here a lower level. So there's not much difference in height, so therefore we can say, or we can neglect, that the potential energy is zero. Okay, what else? What else? The internal energy, right? So the internal energy is actually, we can assume that is zero. We don't have data or information saying that after it after the fluid goes here, it's heated up. Of course, eventually it will heat up, but the heating may not be significant, and it will just pass this pump in a very fast rate. So therefore, there's not much significant heat transfer to the fluid. So therefore, there's no change in the internal energy. Take note, I use internal energy rather than the enthalpy. Okay, so later on you will find out why. Right, so next step is, once everything is set, okay, what else? We also need to assume steady state condition, right? Steady state condition. So that means properties do not change with time. Right, so next step is to apply the energy equation. Apply the energy equation. Okay, so what form? Is it total form? Is it rate form? What else? So since we have per unit time here, we'll be using the rate form. Right, so summation of energy in minus summation of energy out is equal to the rate of change of energy in the system, rate of change of energy in the system with respect to time. But since this is steady state, and therefore the right side is zero, so rate form, we have a dot here, so therefore we can further simplify the equation into energy in is equal to energy out. So that's just it. Right, so what are the energy interactions that's going in? We have work input and this flow input. So work input is, that's what we're solving. Work in, okay, plus F in is equal to F out. So as usual, I want to put this to the right side so that I can just write it in terms of difference. So work input is equal to delta F, right? So F out minus F in. Now what are the terms included in the F in this F term? Recall we have this delta H plus delta KE plus delta PE. So take note again that the F is this bunch of terms here, they're not since my system is this is the pump, so it's not the property of the system, but rather it's the property of the fluid that crosses the boundary, right? So it's not the same thing. So delta KE, there's no change. That means this is zero, this is zero. Now what is H? So H is delta U plus the flow work. So the flow work, since we have a change in so you see delta U is zero, there's no change in the temperature, but the flow work, because whenever a mass moves or crosses the boundary, whether entering or leaving, then there must be some work needed or required for it to flow. So that work is what we call the flow work. All right, so flow work, this is V delta P. Right, so there's a change in pressure, right? Change in pressure so that it can move so that the fluid can move. So the constant volume, and then you have a change in the pressure. Right, so this one is 0, right? So that means that the work input here is just simply V delta B. So that's our main equation, I think, or working equation for this problem. Right, so now let's substitute the values. What is V? It's 8 cubic feet per second times the change in the pressure. Now, what is the pressure? From P2 minus P1, that is 70. Right, so 70 minus 15, and the unit is PSI. That's pounds per square inch. Right, so to check the units, we have a unit of length here. Feet is a unit of length. Inch is also a unit of length. Then we have to convert one to the other. Now, which one? Is it the feet or is it the inch? Now, recall that, anyway, it's just the same thing. Anyway, for me, or what we know so far regarding the unit of energy is the foot pound, right? So foot pound per, and since we are in rate form, that means foot pound per minute maybe. Right, so or foot pound per second. So if we want this unit foot pound per second, then that means we need to convert inch to feet. So how to convert? So times the, right, so times, so let's multiply to the conversion factor. So how many inches are there in a foot? You have 12 inches divided by 1 foot, but this is squared, so therefore we need to square this term. Right, so that's it. Okay, what else? 80 foot. Right, so let's do the computation. So for the computation, we have 8 times, right, 70 minus 15 times 12 squared, or 144, is equal to 63,300, what is this? 63,360 foot pound per second. Right, so let me check again. 15 to 70. Sorry, this is 0.8. So this is not 8. So 0.8. So 0.8. Alright. 0.8 times 70 minus 15. So 6,336. 6,336. What's the unit? Foot pound per second. Right, so we are asked to determine the power in horsepower. So we need to know the conversion of this. So recall that for the conversion, we have 746 watts is equal to 1 HP, and then 1 HP is equal to 550 foot pound per second, and then it's just equal to 33,000 foot pound per minute. So that's what we know so far. So times 550 foot pound per second, that's equal to 1 horsepower. So 6,336 divided by 550. This is equal to 11.52. Okay, 11.52 horsepower. Right, so that's the work input that we need. Of course, we didn't include the efficiencies, but at least we have some values here. Right, so to review in what we did, basically in any analysis, what we can figure out or what we can learn is that we need to be familiar with the systems that we are solving. So that's the reason why sometimes I need to expound the operation of the system so that at least we are on the same page. Right, so first step again in any analysis is to select the system, and then specify the interactions, write the state properties, and also the assumptions. Assumptions actually simplify, so it's not actually just to make the solution easier, but rather make assumptions based on appropriate. Of course, we'll be using appropriate assumptions. Right, like for example, delta PE is approximately 0. There's no change in internal energy because there's not much information, right? So it's not just randomly selecting that we don't want the potential energy, we don't want the kinetic energy, we don't want whatever. So it's not that way, right? So um, once the analysis is done, then apply the energy equation, then just select the appropriate form. Is it weight form, total form, a specific form, and then apply the what we have learned from topic I think topic 2 or topic 1 to topic 6. Right, so it so happened that here we are looking inside this enthalpy term, specifically this flow work. So flow work V delta P. Right, so substitute everything, then check the units. If it's correct, then there you go. You can find what you're looking for. So I hope with these sample problems, I think you now have an overview of how to use these energy equations. Right, so in the next topic will be still in this topic 7, we'll be discussing the conservation of mass.